right, good morning or good afternoon, advanced algebra. I am home with a sick kiddo. She won't stop throwing up. So I am in here Sunday afternoon making a video for you guys to go through the rest of the applications worksheet. There are lots more applications on the website, so I would recommend you take a look there and do some more of those problems. And then since I'm gone today, I'm going to be pushing the test back to Thursday and Friday. Okay, so instead of it being Wednesday, Thursday, it'll be a Thursday, Friday test. Feel free to email me any questions you have. And just so you have a heads up, going into this assessment, any retakes that people will want to do, I'm going to say you have to have the suggested homework done. So, so if you were thinking about doing it and you're not sure, maybe that will be an indicator of maybe get it done before the test. Obviously, you're going to do better on the test if you do the practice. But if you don't do it and you have to do a retake, I'm going to say you have to do it at that time. Okay? So where we left off on Friday, we had talked about from 7.1. Again, this is from compound interest. Something sticky there. The A is the initial amount, R is the rate, N is the number of compounds in a year, and then T is time. So number one was just plugging in the numbers and finding how much you would have after some certain time period. And then number two, we got to various points in different classes, so this is kind of where I want to pick up today. But you have 5,000 at the end. You're starting with 1,000, 3% compounded weekly. So again, we're pulling all of the numbers from the problem, but this time we don't know the t. Okay, we're asked to find how long. So this is considered an exponential problem because the variable's in the exponent spot. So to solve for an exponential, you want to get the exponent term by itself. So we'll divide both sides by 1,000. Okay. So 1,000 divided by 5, or 5,000 divided by 1,000 is 5. We still have all of that the same. Okay. At this point, we just have a term equals a base to a power. So you can either switch to log form or log form. Use the definition of log, or take the log of both sides. You decide which way you like. I like to take the log of 5, and I'm intentionally taking log base 10 so I can plug it in my calculator. Okay. And then 52t log of 1 plus 0.03 over 52. Okay, so what happened here is when you're taking the log of the right-hand side, you have an exponent inside the log, and we have the power rule that says that exponent can come out in front as a coefficient. So I've already done that. Okay, at this point, we're trying to get t by itself. So what I would do is take log of 5 and then divide by 52, and then also divide by this log. So t is equal to log of 5 divided by 52. Okay, and that's because we're getting t by itself. And then we also have to divide by log of 1 plus 0.03 over 52. Okay. This would be considered your exact answer, and then you could plug it in your calculator to get the approximate, which is about 53.66 years. Okay. All right, number 3. Same scenario where it's $1,000, 3%, but now we're compounding continuously. How long will it take to earn 10,000? So with this 1 and 2, it was compounding weekly, and we could use this formula if it was semi-annually, monthly, daily, weekly, hourly. But this idea of continuous, harkens back to what we watched on Thursday with the nonstop, like every second compounding. So there's a new formula, and it's part of the exponential base e, Euler's number. Okay, and what it looks like, I'm going to use a, usually use p, but a e to the rt power. Okay, so e is unbounded continuous growth. So we're saying that's our compounded continuously. Okay, and we saw in the video that it was the 1 plus 1 over n to the n. As n got to infinity, it approached e. So we're basically replacing that part of the formula with e. A is still the initial or starting amount, r is still the rate, and then t is time. Okay, so for this problem, we know that a is 1,000, e, and then the rate is 0.03, and it's asking how long. So we're going to be solving for t, okay, and we're finding when the output is 10,000. Okay, so this is a setup of our equation. Okay, it's similar to number 2 in that it's an exponential equation. So we're going to divide by 1,000 and get 10 equals e to the 0.03t. Okay. From here, what we did was take the log of both sides. We will do that with this one as well, but because it's a base of e, we're going to take the natural log of both sides. I'm going to extend this. Okay, so it's the natural log of 10 equals 0.03t times the natural log of e, and the natural log of e is 1. Okay. So to get t by itself, you just divide by 0.03. So t is the natural log of 10 divided by 0.03. And it's about 76.75 years. Okay, so again, if you need either of these formulas for the test, I will provide them for you, but you should know how to use them, when to use them. Okay, on to our next problem, archaeology. So this is kind of an interesting one. Every living thing on the surface of our Earth has carbon on it. So there's a radioactive substance that comes down from our ozone, and so it touches on anything that's plants or animals, humans. It does not touch anything underwater. Okay, so you can't use carbon dating with like fish, but anything that would have been on the surface of our planet, you can carbon date. So you're considered to have 100% of carbon-14 when you die, and then as as a substance kind of decays over time, it loses that carbon amount. So so you can figure out how much carbon is left in whatever fossil you're looking at, and then use that to date how old it was. So carbon-14 has a half-life of 5,730 years. What that means is if you had started with 100% of carbon-14 when you died, after 5,730 years, you would have 50% of your carbon-14 remaining. Okay, 5,000 years and you still have 50%. Okay, in this formula, okay, in other years I've solved for this kind of decay rate. We're going to skip that for this year, but the A is the initial amount of carbon. So typically we use 100 for 100%. E is that unbounded growth, but because we have a negative rate, that's what's causing it to be a decay factor. And then T is our time in years. So we have a paleontologist examining bones. Only 2% of the carbon-14 remains. So the 2 is going to be the Y because that's the ending amount that we have. So it's 2 equals, and we had started with 100%, e to the negative 0.000120968t. Okay, we're going to solve for t. This should look a lot like number 3, right? Okay, so divide both sides by 100. You get 0.02 equals e to the negative crazy small number. Okay, what this is telling you is really we could have, instead of using 100% and 2%, we could have used 1 as the decimal form of 100% and then 0.02, and it kind of saves you a step. So if you want to just start at this step, that's perfectly fine. Okay. From here, we're going to take the natural log of both sides, and that's because we have a base of e. So it's the natural log of 0.02 equals the exponent times natural log of e, which is just 1. Okay, so to get t by itself, we'll divide by that really small number. So t is the natural log of 0.02 divided by negative 0.000120968. Okay. And you're going to get about 32,339.3 years. So the fact that this animal only had 2% of its carbon remaining means that it's about 32,000 years old. Okay, so carbon dating is kind of a really interesting thing, and it's related a lot to E and the natural log in the solving process of how to figure out how old something is. Okay, 2 more problems. The U.S. population in 1950 was about 152 million. And it has doubled between 1950 and 2010. That is true. I looked it up. Okay. If this rate continues, in what year will the population reach 1 billion? Okay. Let's hope our population doesn't get that big, right? There will likely be some sort of natural resources that are hindering us, or just our square miles that we have in the U.S. But if this population continues at this rate, we're wondering how long would it take. Okay, so this harkens back to just a generic exponential equation, y equals a times b to the x. I know that because it doesn't really fit this compounding with finance, and it doesn't fit our continuous compounding. It's not like we're given a formula. Okay, so we have to kind of build this one ourselves. A is the initial amount, and then B is the growth rate. So I know the initial amount is 152 million, and what we're doing is assuming that X is years since 1950. Okay, that'll save us a little bit of work so that X doesn't represent years since 0. Okay. And the rate, so B is the constant multiplier, and we know that we're doubling, right? So B is going to be 2. But the X is kind of weird. So it's not that it's doubling every year, right? So if we just put X, that would say, after 1 year in 1951, we've doubled. And that's not true. It's actually, what would it be, 60 years? So there's a 60-year gap that it's doubled. So I want it to be that if it's 2 to the first, it represents 60 years. So if I divide my X by 60, then I'm going to get my doubling time every 60 years. Okay, so what I mean is, let's try this out. 2010 is 60 years from now. If we put in 60 here, 60 divided by 60 is 1. So 2 to the first is that we've doubled 1 time, and that's what the problem is telling us. So if you have a doubling time that's not like every minute or every day or every year, you just divide by how long it took you to double. Okay. So we're wondering when it will reach 1 billion. Well, our X is in, I guess our Y we want to represent in millions, right? And that's because we're not going to be adding all these zeros to 152. So how many millions are in a billion? There's 1,000, right? So I'm going to put 1,000 equals 152 times 2 to the x over 60. So this is our exponential equation we're going to solve. Like before, we have to divide by that a value. So 1,000 divided by 152 simplifies to 125/19. And the reason I'm not going to give a decimal here is because I'm approximating, and it's important that you keep your work as exact as possible until that very last step. Otherwise, your answer could be rounded, by as much as like a decade, if we're talking about this. So keep your answer. You could keep it as 1,000 over 152, but it just reduced. So I thought it was easier to use smaller numbers. Okay. Now we're going to take the log of both sides. So log of 125/19 equals x over 60 times log of 2. And again, when I took the log of the right-hand side, I brought the power out in front. And I didn't have to use natural log because I didn't have a base of e, so I'm just using the common log base 10. Okay. To get x by itself, I'm going to multiply both sides by 60. So it's going to be 60 times log of 125/19. And then I would have to divide by log of 2. That's the exact answer. The approximate answer is 163 years. Okay, so is it 163 years from today, like 2019? It's not, right? We had said X is the year since 1950. So if we did 1950 plus 163 years, we would get the year 2113. So give it about, what, 95, 96 years? And we'll get there. Gosh, I hope we don't get to 1 billion in the US. All right, last question. A bacteria grows by 15% each day, and how many days will it be twice the original amount? Okay, so this is another one where we have to kind of set it up. Y equals a times b to the x. But we're not given anything about the initial amount. Okay, so for now, hold on. We'll just leave it as A. Okay. But the B, we're growing by 15%. So it's kind of like the compound interest. It's 1 plus 0.15. Okay. And the question is asking in how many days. So X is the oftentimes the years or the days or the time period. So we're going to be solving for X. So that means we must be able to figure out some numbers we can use for A and for Y. So A is the starting amount, and then Y is the ending amount. And it's asking in how many days will it be twice the original amount. Okay. Well, the cool thing is you can decide whatever you want for A. You can use 1, you can use 100, you can use 36, like whatever number you want. And then just make sure your Y value is double whatever you chose for A. Okay, that way you're ending with twice what the original amount is. So I'm going to be lazy here and just make my A value 1. So that would make my Y value 2. Okay. By making it 1, I'm saving myself a step. Okay. I wouldn't have to divide, because if you had 200 and 100, you would have to divide by 100, and then you'd still get to the same step that I did. Okay. Think about what you would do from here to solve for X. You can either switch to log form, or you can take the log of both sides. We've done several where you take the log of both sides, so let's do this one where you write it as a log. Okay, it's the exponent equals log base 1.15 of 2. You can use the change of base then to write it in a form that your calculator will accept. Log of 2 divided by log of 1.15. So what we're doing is using the change of base to write it as base 10. This is approximately 4.96. So our answer is in how many days? Well, it's going to be about 5 days. All right, that's it. Make sure you guys are doing a lot of practice, and then I will see you tomorrow.